Hi, my name is Adrienne Roller, and I will be doing my honors capstone defense on cyclic voltammetry and the synthesis of copper photoredox catalysts. So I'm going to start with a little bit of background on photoredox catalysis. A catalyst is a substance that increases the rate of a chemical reaction. So when a chemical reaction is taking place, it takes a certain amount of energy to convert the reactants into products. Using a catalyst lowers the amount of energy that's necessary. So photoredox catalysis is based off of the reactions that take place during photosynthesis, where chlorophyll absorbs a photon of visible light and promotes an electron to a higher energy state. This excited state electron can then be donated, triggering a cascade of electron transfer reactions that results in the formation of glucose, which is an energy source. In photoredox catalysis, a synthetic catalyst is used to absorb visible light, and this excited state electron can again proceed through an electron transfer reaction. The end goal of this, however, is not the storage of energy, but the formation of new chemical bonds. The use of photocatalysis in organic synthesis has allowed chemists to unlock unique reaction pathways that are highly selective due to the free radical nature of them. These reactions are biocompatible and operationally simple, plus the use of visible light is non-toxic and environmentally friendly. Because of this, photoredox catalysis can be particularly useful in pharmaceutical development. One company included these three examples of the types of photoredox reactions that had the most significant impact in medicinal chemistry. So, Doyle and Macmillan in 2014 linked a carboxylic acid and an aryl halide to create an alkyl aryl product. Molander in 2014 did the same thing, only with a trifluoroborate and an aryl bromide. And then Macmillan in 2016 used an alkyl bromide and an aryl bromide to get the alkyl aryl product. The catalysts that are traditionally used for these types of reactions are iridium or ruthenium complexes, and while they are efficient due to strong visible light absorption and long lifetime excited states, they are expensive and toxic. Because copper has similar photophysical properties, it was hypothesized that copper complexes could function in the same manner and replace the ruthenium and iridium complexes. Copper complexes were found to be successful in various organic synthesis reactions and have the added benefit of being more abundant and less expensive than the traditional catalysts. Reduction potential is a measure of how easily a compound gains or loses electron. Specifically, reduction is the gain of electrons, while oxidation is the loss of electrons. The purpose of a photoredox catalyst is to start a chemical reaction by donating an electron, so reduction potential is an important factor in catalytic efficiency. Reduction potentials are often displayed in a table of standard potentials from strongest to weakest oxidizing agent or vice versa. Changes to ligand structure of the copper catalysts may affect the properties of the catalyst. Ligand refers to the molecule that is attached to the central copper atom. Making the R groups more electron donating or electron withdrawing may affect the reduction potential and therefore the catalytic efficiency. A methyl group, for instance, is more electron donating, where a fluorine atom would be more electron withdrawing, meaning that it draws electrons away from the reaction center. So next we're going to talk about some background of cyclic voltammetry. To collect the data and conduct the experiments, an electrochemical cell is used. Within the cell, there's a mixture of solvent and supporting electrolyte, and the solvent is used to dissolve the analyte, or the chemical species that's being investigated. The electrolyte solution assists in balancing charge and increasing solution conductivity. The cell is fitted with 3 electrodes, a reference electrode, a working electrode, and a counter electrode. The reference electrode has a reliable electrode potential and provides a reference point in an electrochemical cell that other electrodes can be measured against. The working electrode is where the electrochemical reaction takes place as a potentiostat is used to apply a voltage to the electrode. The counter electrode completes the electrical circuit, allowing current to flow as the working electrode reduces or oxidizes the analyte. The cell is connected to a potentiostat, which supplies a voltage and measures the resulting current as electrons flow from working electrode to counter electrode. The electrons move due to a difference in energy levels, where the applied energy causes the electrons in the working electrode to move from the highest occupied molecular orbital, or HOMO, to the lowest unoccupied molecular orbital in the chemical species, or LUMO. This is possible only when the LUMO of the species is lower than the HOMO of the electrode. The redox data is recorded in a graph called a cyclic voltammetry. It shows the applied potential in voltage on the x-axis versus the resulting current in amps on the y-axis. Various parameters can be altered to fit the experiment, including scan rate, starting potential, and final potential. If potential is swept positively or anodically, the analyte in solution reacts with the electrode, forming a peak in the voltammetry, which indicates oxidation. At the switching potential, the direction is then reversed and the potential runs negatively or cathodically, which forms another peak, indicating reduction of the analyte. The voltage at which these peaks occur can be used with the Nernst equation, which is at the bottom of the screen, to estimate the reduction potential of the analyte. The potential at the peak of the cathodic trace is denoted EPC, while the potential at the peak of the anodic trace is EPA. The average of those two values is referred to as E1/2, which is approximately equal to the formal potential. And the formal potential represents the reduction potential under experimental conditions in the Nernst equation. The Nernst equation is used to relate the standard potential to the reduction potential, temperature, and concentrations of a chemical species. So CV can be used to measure reduction potentials, but it can also be used for determination of reaction types, antioxidant capacity, concentrations, and HOMO and LUMO of compounds. So next I'm going to go through the experimental portion of my project. The CV experiments were conducted with the ICA Electrocin 2.0. So a 3 molar KCl electrolyte solution was made to fill the glass tube of the silver wire electrode, and it was soaked to make sure that the solution was permeated throughout, which ensures that there's a good current and salt flow when you take a CV. To test the instrument, a 0.01 molar solution of a compound called Tempo was prepared. The electrochemical cell was assembled with the silver wire electrode as the reference electrode, a glossy carbon electrode as the working electrode, and a platinum electrode as the counter electrode. The vial was filled with the Tempo solution so that the tips of the electrodes were submerged, and then the CV was taken. A solution with a ruthenium catalyst was also prepared and tested, once with sparging with nitrogen and once without sparging. And sparging is when you bubble gas throughout a solution in order to remove other dissolved gases. In this case, dissolved gases such as oxygen could affect the oxidation or reduction, giving inaccurate CV results. So this is the resulting CV of the tempo test. The current was swept anodically, which produced a peak indicating oxidation around 1 volt, and the reverse cathodic trace shows a peak indicating reduction around 0.6 volts. The results of the ruthenium catalyst show that there are significant differences between the sparged and the unsparged solutions, indicating that future experiments should be done after bubbling through with nitrogen. The process of doing the ruthenium CV was stalled and took longer than expected because we had problems with data collection. So we moved the research towards the synthesis of some of the copper photoredox catalysts. So the steps are shown here for the ligand synthesis of the copper complex. The purpose is to add the CF3 group, which is electron withdrawing to the ligand, to see how it changes the complex's overall properties. So 2,9-dichloro-1,10-phenanthroline and 4-trifluoromethyl phenylboronic acid dissolved in toluene and an aqueous solution of sodium carbonate were added to a reaction flask. The reaction was very air sensitive, so the mixture was sparged with nitrogen before addition of a palladium catalyst. The reaction was heated to reflux and then stirred for 24 hours. The product was collected and examined using thin layer chromatography and then purified using column chromatography. The product was then characterized by using fluorine, carbon, and proton NMR. So NMR can be used to identify molecular structure of a sample by comparing the size and location of the peaks that result from the test. This fluorine NMR shows a peak at -63 parts per million, which is where the chemical shift should occur for a CF3 group. This carbon NMR looks at carbon atoms within the molecule, and the peaks matched with the ligand we were trying to make. And this proton NMR looks at hydrogen atoms within the molecule, and the positions of these peaks also match with the ligand. So because of these characterizations, we believe that the ligand synthesis was successful with a 41.6% yield. Next, we used the ligand to synthesize 2 copper complexes. The first one contained a chlorine counterion used to balance the charge of the positive molecule. Both the free ligand and copper chloride were added to a flask with double the amount of ligand as copper chloride. Sparged methylene chloride was added to the reaction flask, and the reaction stirred for 30 minutes, and the product was then dried. The second complex contained a PF6 counterion. This complex was synthesized in the same way, except tetrakis copper 1 hexafluorophosphate was used instead of copper chloride. NMR was used for characterization of the complexes as well. However, both complexes show impurities. Because we are not adding any new hydrogen atoms, but only doubling the amount of the ligand, the NMR of the ligand and the complex should look the same. For the proton NMR, all of the hydrogen atoms are connected directly to the ring structures on the molecule called aromatic rings. These aromatic hydrogens should show up in the aromatic region, typically between 6.5 and 8.5 parts per million. So all of the peaks that are outside of this range indicate impurities in the sample. Attempts at purification were made on one of the complexes. The left NMR is after the first purification attempt, where there are still peaks outside the aromatic range, but the size of those peaks is reduced. And the right NMR is after the second purification attempt, where there are additional peaks in the aromatic range indicating some ligand dissociation. So the peaks indicate that the catalyst was produced, but impurities are present and attempts at purification were unsuccessful. So going forward, next steps would include resynthesizing the catalysts, taking more precautions to avoid contamination, and if synthesis is successful, then the catalyst can be tested in a reaction. Now that the instrument is set up, previously synthesized and newly synthesized catalysts can be examined using CV to gain knowledge about their electrochemical properties, specifically reduction potentials. And that is the end of my presentation. Thank you for watching, and if you have any questions, feel free to email me using the email that is on the slide.